Okay, let's dive right in. Triple integrals. I know the name alone can sound a little intense, but what if I told you there's a way to make some of the most complicated 3D volume problems, well, surprisingly simple? Today, we are unlocking the power of spherical coordinates. I mean, really think about that for a second. Try to picture setting up the bounds for the volume of a sphere using just x, y, and z. You're going to be wrestling with square roots and all these messy inequalities. It's clunky, it's not fun, and it is exactly the problem spherical coordinates were invented to solve. So here's our game plan for this explainer. First, we'll cover why we even need this new system. Then we'll get to know the three key players in spherical coordinates. After that, we'll look at the single most important conversion factor. You don't want to miss that. We'll run through two classic examples, and then we'll wrap it all up with a toolkit you can take with you. So, first things first, why even bother learning a whole new coordinate system? Well, look, in calculus, just like in life, you get much better results when you choose the right tool for the job. And this slide says it all, really. Cartesian coordinates, x, y, z, they're fantastic for things like boxes, cubes, straight lines. But the second you deal with something round, a sphere, a cone, a planet, it just becomes a nightmare. A sphere in Cartesian is x squared plus y squared plus z squared equals r squared. In spherical, it's just rho equals r. That's it. So simple. This is the elegance we're about to tap into. All right, so let's get properly introduced to this new language. From now on, every point in space gets a new three-part address: rho, theta, and phi. First up, we have rho. This one's the easiest to get. It's literally just the straight line distance from the center of everything, the origin, straight out to your point. Just think of it like a 3D radius. Next is theta. And hey, if you've ever used polar coordinates, you already know this one. It's the angle that sweeps around horizontally, flat on the xy plane, kind of like longitude on a globe. A full circle is 0 to 2 pi. And here is our new player, phi. This one is so important. Phi measures the angle down from the positive z-axis. Think of it as the North Pole. So phi 0 when you're pointing straight up, it's pi over 2 at the equator, and it's pi when you're pointing straight down at the South Pole. That's the entire range, just 0 to pi. And here they are all together in one place. Rho is your distance out from the center, theta is your rotation around, and phi is your angle down from the top. If you've got these three, you can find any point in space. Okay, deep breath. This is important. You can't just swap your old volume element dv for d rho, d phi, d theta. It's not a one-to-one trade. When we change coordinate systems, we have to account for how volume gets stretched and squished. And that brings us to the single most important piece of this entire puzzle. And there it is. The volume element, dv, becomes rho squared sine of phi d rho, d phi, d theta. This isn't just a friendly suggestion. This is the key that unlocks every single triple integral in spherical coordinates. You have to include this rho squared sine of phi term.
I really can't stress this enough. This is, without a doubt, the #1 mistake people make. They do all the hard work of finding the right bounds, and then they just forget to include the conversion factor. So please burn rho squared sine of phi into your memory. Okay, enough with the theory. Let's see how this thing actually works. We're going to start with a classic, proving the formula for the volume of a sphere. This is the perfect first example because we already know the answer we should get, right? And for every single one of these problems, we're going to follow a simple, repeatable three-step plan. Step 1, figure out the bounds for rho, phi, and theta. Step 2, write out the complete integral. And step 3, solve it. So for a sphere of radius r, what are the bounds? Well, let's think. The distance, rho, goes from the center, 0, out to the edge, r. To cover the whole sphere top to bottom, phi has to go from the North Pole, 0, all the way to the South Pole, pi. And to go all the way around, theta has to make a full circle, 0 to 2 pi. See? It's pretty intuitive. Now we just build the integral. We put in our bounds that we just found. We're integrating the function 1 because we're just finding volume. And, most importantly, we include our conversion factor, rho squared sine of phi. That is the complete setup. Now for the fun part. Since our bounds are all constants, we can just solve each little integral separately. The integral for rho gives us r cubed over 3. The integral for sine phi from 0 to pi gives us 2. And the integral for theta gives us 2 pi. Multiply them all together, and what do you know? 4/3 pi r cubed. The formula we all know and love, derived right here from scratch.
So cool.
Feeling confident?
Awesome. Let's kick it up just a notch with another classic problem, the ice cream cone. This is where you can really see how powerful spherical coordinates can be. So here's the problem. We need the volume of a region that's got a sphere for a top and a cone for a bottom. Let me tell you, trying to do this with X, Y, and Z would be an absolute mess. But with our new toolkit, it's totally manageable.
Okay, let's find our bounds. The sphere's equation tells us the max radius is the square root of 4, so rho goes from 0 to 2. We still need a full revolution, so theta is still 0 to 2 pi. The tricky part is the cone. The equation, z equals the square root of x squared plus y squared, that's the line where the height z is the same as the radial distance r, and that specific angle is phi equals pi over 4. So our phi bound just goes from the top, 0, down to the edge of the cone at pi over 4.
And check this out, the setup looks almost identical to the sphere problem. The integrand, the order we integrate in, it's all the same. The only things that changed were the upper limits for rho and phi to perfectly describe our new ice cream cone shape. The rest of the process is exactly the same. Okay, let's bring it all home and put everything we just covered into a final toolkit. These are the absolute core ideas you need to have down to solve these problems on your own. Here are the essentials. First, know when to use this tool. Anything with spheres and cones. Second, know your coordinates like the back of your hand. Rho is distance, theta is around, phi is down. Third, one last time, never ever forget the volume element is rho squared sine of phi, d rho, d phi, d theta. And finally, stick to the plan. Bounds, setup, solve. And here are the traps you need to watch out for. We've talked a lot about forgetting the conversion factor. Another big one is mixing up the ranges for theta and phi. Remember, theta goes all the way around, 0 to 2 pi, but phi only goes top to bottom, 0 to pi. And finally, getting the phi angle for shapes like cones can be tricky, so that's where you'll want to practice.
So there you have it. We've taken a pretty complex tool and broken it down into a clear, repeatable process. You now have this incredibly powerful way to calculate volumes for shapes that used to be almost impossible. The real question is, from physics to computer graphics, what amazing problems are you going to solve with it?